Good morning. Thank you very much for getting out of bed early, despite the after party and all the beer, to come to this talk. Thank you also very much to the organizers and the PC of Lambda Days for inviting me to this wonderful conference in beautiful Krakow. And so today, I'm going to talk about blockchains. Now, when you mention the word blockchain, you get all kinds of responses from wild enthusiasm about a new world order to deep skepticism about internet scams, cryptocurrency speculation, and everything in between. So what I want to start out with today, I want to motivate why it's a technically interesting area and why it is also very challenging. And moreover, why it really screams functional programming. And in particular, I want to outline the work which we've done in our team on a Haskell-based programming language for a particular blockchain. And how this all relates to a research-driven development process, which is what is being implemented at IHK, where this work has been done. All right, so let's start with the basics. Let's suppose we have 3 people, Alice, Bob, and Charlie, and they want to exchange some funds. So they keep track electronically, of course, 2019. So they keep track of their own balance, and maybe Alice sends something to Bob, and Bob sends something to Charlie. But you may wonder, how do you know they're honest? I mean, everybody could just change their own little local number, right? So, well, there's a standard solution for this. You use a bank, right? So, technically speaking, you use some sort of central server, authority, whatever. And instead of actually maintaining your own local balance, you delegate that work. And you now, a transfer means you tell the authority about what you want to do. Now, we are already in a kind of distributed setting because these messages come to that central authority at times which are maybe not fully under our control. So we could get into ordering problems. So for example, if Bob is a little too fast and he sends his request, then that's too early. The funds from Alice haven't arrived. Now this transaction is invalid. What are we going to do about this in the first place? Also, well, distributed computing, if you've ever given a lecture or sat in a lecture on distributed computing, the first thing they tell you, don't put into a central server into the system because it's going to be your bottleneck. So also, how do we know that Charlie isn't going to hack into the thing? And so there are issues to consider here. So the idea behind a cryptographic ledger is to use some fancy cryptography, the same technology which we use for encryption, and instead of just keeping a record of the current balances, to actually keep a log. So it's a bit like a log-based file system, if you like. So whenever we have a transaction, we just append that transaction to the existing record, and we do that in a way using some cryptography, which I'm not going to go into here, to make sure this is an immutable but still verifiable log of what happened. So when you hear the word immutable, you should go like, yes, 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 because functional programming. All right, so this is good. We are moving in the right direction. But once we've got this data structure, why only send money to one another? That's boring. So we could store some other information. For example, well, why do you send that money? Well, that's still easy. How about doing something more fancy? For example, maybe Alice is actually growing timber and Bob is producing things from timber. Then, well, in Europe, there are a lot of regulations about where you can get your timber from and when you can call it sustainable or ecological sourced and so on. So maybe we can record this type of information. For example, Alice could, when she sends a shipment of timber over, record on the blockchain in this transaction log a DNR hash of that shipment, and make this part of the log. And then somebody who consumes it can refer back to that in whatever they make out of this original resource, and in that way prove its origin on a public ledger. Now, once you're doing this sort of things, then all kinds of new technical questions arise. So, for example, once we were only talking about money, it was clear when a transaction is valid. But now in this case, we need something, a custom sort of validation. How do we know this orange back arrow is valid? Why is this timber something I can use? So I need some custom code here. But I don't only need custom code to do this validation, I also need code to create the transactions, to process all the external resources, and so on. So, wow, now we need an entire programming language. Even better, like I'm a programming language researcher. That's the kind of thing which gets me excited. Okay, so programming language. Now, if we look at this problem in a bit more detail, we see, well, yeah, it's programming language, but there's also a lot of distributed computing in here. So these on-chain scripts, they are processed on some servers. In fact, it's the same servers which maintain those cryptographic ledgers, because these scripts are part of the validation of whether a transaction makes sense or not. But all the other processing happens in maybe Alice's computer, Bob's computer. It's a kind of client side. So we get a kind of client server. It's a little bit like writing a web app, right? With the blockchain being your backend and the on-chain processing being your backend code of the web app. So now we are getting into this situation, but it's even trickier because, well, the infrastructure that runs that backend is not just one computer with one IP address, actually a set of computers which together build this log data structure. And they have to do this in a manner that they are everybody is sure everybody is playing by the same rules. So how do we ensure these rules? Well, that's why it's called a cryptographic ledger. We need some cryptographic proof. And they're attached to each transaction. And there are basically two ways of getting that proof, which are kind of discussed these days. So one is what's called proof of work. And proof of work is the idea on which early systems like Bitcoin and the Ethereum blockchain are based. And there's a big problem with that. It needs a hell of a lot of energy. I mean, I'm sure you've all read the newspaper articles about Bitcoin uses as much energy as, I don't know, whichever country. So that's bad, very bad, like global warming. No, we don't do that. So the alternative is what's called proof of stake. So instead of solving a cryptographic puzzle, which takes a lot of GPU cycles, we actually look at each contributor's investment into the system and use that to decide who can create blocks for that verifiable log, for that blockchain. And that's much more lightweight, but it's technically also way more complicated. But to give you an idea for how lightweight, some of the engineers doing the core node development at IHK are talking about maybe putting a node on a Raspberry Pi. So it's really lightweight. All right. But then cryptographic proof, we are not cryptographers. Well, let's trust those people. I mean, they do their protocols in the open. Let's suppose all this cryptography works out, because if it doesn't, we are kind of in a bad place anyways. So, but how about all this code? Like, the cryptography is hard. Somebody has to implement that. Ooh. And then there are lots of protocols. It's a distributed computing set up with messaging, everything. Ooh, even harder. And somebody implements that all in what and where. So in order to be able to trust such a system, we really want to be sure all these bits and pieces come together. And the way to do that, the only way we really know how to do that, well, is to use math. So we need some sort of formal methods, high assurance development methodology to get some sort of assurance that this stuff is actually doing what it's promising to do. All right, so to summarize, we are creating a cryptographic ledger as a distributed log immutable data structure. In order to do something more interesting than just pushing money around, we need some computing facilities which are split between computing which happens on the blockchain creating servers and do some validations of transactions and also some client-side computation. And then we really want a system which doesn't contribute to global warming on a huge scale. And we need to build it in a way that we can actually be reasonably sure that it's actually working properly. That's a tall order. So let me tell you a little bit about the Cardano blockchain, which is what's called a third generation blockchain, because Bitcoin, number one, Ethereum, number two, and you get the idea. So Cardano is based on proof of work. And it's designed to be scalable in the sense of that the number of transactions can increase to the kind of levels that are necessary. But it's also not an isolated system because, I mean, there's all kinds of work on blockchains, and if they can't talk to each other, that wouldn't be very good either. And also we have to think about how these systems evolve. It is, again, a very headline situation where you have forks in Bitcoin or Ethereum, and then people get very upset. And I mean, you've all read those stories. So there needs to be a somewhat more sensible system here. And also, it needs to be sustainable. So a lot of these efforts, they use some kind of token sale, get rich quick scheme to get some money and build something, and then they run away. So how can you build such a system in a way that it's actually sustainable in the long run without any strange internet scams? So to do this, really, we need a lot of research because even on the cryptographic level, this stuff is very complicated, but also the implementations are quite complicated. And in the case of Cardano, we make a use of a lot of function programming technology, which is why I'm here. So let's focus on these two things, right? We are not cryptographers, we are function programmers. So I already motivated for doing things like this proof of stake scheme, which is sustainable from an environmental point of view, but cryptographically much more complicated. We need to do cutting-edge new cryptography. But we also have to develop formal methods to turn that into actual code. So there's a lot of scope for research here. But then we've got a paper, ideally published at a nice, prestigious venue. That's a long shot from having code you can actually give to somebody who wants to use that system. So how can we connect the two? And that's where formal methods come in. So we use a formal methods-driven approach to doing an implementation in a functional programming language. So about the research, for example, talking about this proof of stake system, the algorithm which underlies Cardano is called Ouroboros, and IHK is involved in the blockchain research lab at Edinburgh University, run by Argelos Kiaias. And his group, they are working on the cryptographic side and coming up with all these clever cryptographic algorithms, including proof of stake, but also interoperability, scalability, all this stuff. But IHK is also involved in a lot of programming language research. So for example, there's a collaboration with Simon Thompson from the University of Kent, who is looking at taking a financial domain-specific language in the spirit of the ICFP paper by Hébert and Peyton Jones and Stuart about having a DSL for expressing financial contracts on top of such a blockchain programming language. And if you're interested in any of that research, here's a URL where you can get some more information. All right, so good. We've got either IHK employs a lot of researchers, they have a lot of collaborators with a lot of researchers. So, okay, we got the science under control here. What's the next step? Well, the next step is to sit down, take these research papers, and extract the essence of the algorithms and the protocols and so on behind them. And that typically happens in the form of fairly simple math, set theoretic stuff, which we write up. And just to pick a little example, you get simple set calculations like that. Okay, so that's a little bit easier to digest than a cryptography paper. If you don't believe me, read one of these cryptography papers. And now this actually, I mean, if you squint at it, it could be Haskell, right? And that's actually the next step. The next step is to write some Haskell code, which, well, we use a record here instead of a pair in the mathematical formula. But if you look at those two, the code and the LaTeX, it kind of makes sense. They fit together. In both cases, we have some helper functions. Now, if we look at those in the specification, they're again expressed over sets of various things. And that Haskell code, again, if you look, the LaTeX uses all kinds of fancy symbols, so it's more compact and so on. But still, if you sit down and you look closely, you can convince yourself, well, that Haskell code, that's about doing the same thing. Looks all right. Okay, it's not formal verification here, but you get a good sense of that they are doing the same thing. So this gives us an executable specification of these various algorithms in Haskell. Now we can run it. It's not fast, it's not distributed, but we can run it. That's the next bit. So now we take this Haskell code, which implements the ideas, and a team of engineers takes that and refines it. So this particular code here is from the wallet backend, like the stuff which runs on the client to maintain the local funds. Now, this wallet backend code, it has to deal with all kinds of things. It has to be incremental. Like new transactions come in, it has to update some data structure. It has to deal with rollback, which is to do with the how these cryptocurrency protocols work, and so on. Then there are networks. It has to persist stuff in a database. All these things. That makes the code much more complicated, much harder to see that it still corresponds to this mathematical description of the algorithms. So what do? Well, we go to John. And he tells us about property-based testing and how we can use a model of the software we want to implement to test the real implementation against that model, which is where we can convince ourselves much more easily that it's doing the right thing. And in fact, John does that. He's involved in some training courses helping IHK engineers use property-based testing correctly. Because as you saw yesterday in his talk, sometimes it's not that easy. So this methodology, if you're interested in more details about it, because it's really a general methodology of doing a research-driven implementation effort, there's a talk by Duncan Coutts, which is on YouTube at the URL from last year, where he talks, gives more details about it. All right, so we have these ledgers we want to build, and we want to use functional programming because we think it's the best technology. So how can we make the ledger representation more functional? That's our core data structure. Well, if we look at that original ledger we discussed, we've got these accounts, we've got these transactions, and then as a user, you're interested in what's your balance. So you tally everything up. Okay, well, remember these first-year courses about object-oriented programming? They either had you implement some exercises with animals, which never made any sense to me, or they go on about accounts. So it doesn't sound terribly functional at this point. So let's go back in time. Let's not think about online banking. Let's think about, remember there are these things, these like little pieces of paper with numbers on them, and you can give them to people and you get something for it. Like I heard that was a thing at some point. So let's take this as a model. So let's suppose you've got this cash, or these individuals in this transaction, and now Alice wants to pay 42 ADA. ADA is the currency of the Cardano blockchain, so that's why I'm using it as an example. So wants to pay that. Then she only has 100, so she needs to get some change. Okay, so we have to split it up somehow. And then Bob, well, in order to do his next transaction of 50 ADA, the original 10 ADA isn't sufficient. He needs to take what he got from Alice and combine the two, and then pay with that, but also getting some change. So what's happening here is we are building a data flow graph of these transactions. And these transactions can have multiple inputs and multiple outputs with different participants in all the various inputs and outputs. And what does it mean for somebody to own any of those funds? Well, what does it mean to own some money? It means you can spend it. So if you can prove cryptographically that you are able to spend a particular output here, then you are the owner, whatever that means. So that's an alternative representation of this graph, and you may go like, this is very different. This is not going to do the same thing. Maybe it is. Well, that's what we got the science for. So I'll get to the science in a moment. Terminology, these outputs, the funds which haven't been spent yet, they're called unspent transaction outputs. That's a term I'll be using all the time, so I want you to know it. But what about the science? Is this really, does this match up? So we got the formal methods team produce a paper about it, and there is an interesting correspondence between the two, and if you want to know all about it, well, read the paper. All right, so now we've got this technically quite sophisticated problem where we need research and research-driven development process to make any significant progress to an implementation which we are confident that it's actually doing what it's supposed to do. So let's look at programming languages. Because as we discussed, if you want to do some more interesting applications than just pushing around money, then you need custom code to validate your transactions, and you need custom code to maintain the incoming data, create transactions, to react to transactions, and so on. So that's exactly, to develop this kind of technology, that's exactly what the Plutus team, which I'm heading together with Phil Wadler of the University of Edinburgh at IHK, that's exactly what we are tasked with doing. And I want to tell you a little bit about what we came up with. So the system is called Plutus, and it's built on 3 premises. So number 1, been going on about this for a while, and if you know me, I'm going on about this all the time, like this functional programming thing. This is really the core of not only our development methodology, but also the programming approach here. So we use functional programming and associated formal methods very heavily in the process to get something where we are confident that it's doing the right thing, but where people who use our system can also gain confidence that they're writing the right code. Because if you've, again, read the headlines, people writing stupid code on the internet for blockchains is kind of a thing. And if you look at the programming languages involved, who has ever written a Solidity program? It's awesome, isn't it? It's like this Frankensteinian version between JavaScript, Python, and some unidentified bits. And yeah. Semantics, anybody? All right, so we try to actually have programming languages where we know what they're doing. All right, and then we are using this functional ledger architecture, using these unspent transaction outputs, which are really functional representation of the ledger. And that's very useful, coming in very handy. And also, we are thinking not only about the code which does the validation of the transactions, that on-chain code, but also how it integrates with the off-chain code. And you'll see in a moment, existing systems do that in a very ad hoc way. So let's look at these three things in turn. So functional programming, not only functional programming, but very heavy use of type systems and dependently typed tools such as ACTA, which are very heavy in our kind of tool set. And for you folks, I don't have to espouse the virtues of functional programming. I think we are already on the same page. It's easier to reason about it. Types give us additional information about what we can use our code for, and it allows the use of these formal methods or formal and semi-formal development methodologies. And that's in this domain just very important in order so that we know exactly what this validation code is doing and that we can find any exploits in it. So let me give you an example. These scripts, these validation scripts, which are run on the servers to check that the transactions actually are valid, we have to represent that code somehow. So typically, if you look at, for example, Bitcoin, Ethereum, all these systems, people use a bytecode. I think the only reason they all use bytecodes is because Bitcoin used a bytecode and then everybody went, this is what we have to use. So we don't do that. We use a type functional programming language because we can actually talk about what the programs mean. You see, I'm repeating the same thing over and over. And it also means we don't need a classical setup of a virtual machine, which again is a complicated piece of technology, which is very easy to get wrong. I mean, how often do you get browser patches for your JavaScript virtual machine or something, the JVM? This stuff basically never works correctly. That doesn't seem a good basis for code which should validate transactions which maybe are sensitive. So what we are using instead, we are using an abstract machine in the sense of programming language theory abstract machine, of which we know what its behavior is. Specifically, what we use for the representation of code on the Cardano transactions, we are using a system called System F omega with recursive types. So you all know type lambda calculus, I'm sure. So System F is a particular form of type lambda calculus, and using the omega, we get a more fancy type system, essentially. So that's great because now we can actually put the entire operational semantics of that core language on one slide. Now, there's a specification of the Ethereum virtual machine, which, well, you can argue about how much it really specifies the Ethereum virtual machine, but look at how long that is, and then tell me you understand what's going on. With this, you have a chance to actually understand what's happening. And moreover, in the same way as I showed you before, how we can go from LaTeX to Haskell in a way where the two are close enough in their structure that it's reasonable to convince yourself the Haskell is implementing that LaTeX, we can do the same here. So our Haskell implementation of that abstract machine actually follows, it uses the mass as comments, and you see the Haskell code really is structured in the same way. So that gives us a lot more confidence in that it's actually doing what it's supposed to do. But not enough. We've got one of the team members, James Chapman, he's really good with ACTA. So he came up with the formalization of the meta theory of System F omega in ACTA, showing the various properties you want to show about such a system, such as the typing properties, progress, preservation, formalization, the operational semantics, all this stuff. And that's good. That gives us additional assurance about what this code is doing, but it doesn't immediately tell us anything about our implementation. So in order to fix that, one of the things we are in the process of doing is extracting an executable version of the code from the ACTA specification and using that in our continuous integration pipeline to test the implementation against. So that gives us a much higher assurance that we are doing the right thing. Okay, so when I say we are using functional programming, that doesn't just mean we get a function programming language and write our programs as if nothing had happened. We really use it in the whole development process to go from specification to implementation. All right, so where is this Bluetooth core thing used? Let's look at the ledger. Now, I mentioned before, we've got two different major ledger models. So one is based on this data flow graph, the unspent, based on these unspent transaction outputs. And the other one is an account-based ledger, which is kind of what you have at your bank. Now, interestingly, if you look at them, data flow graph obviously is a functional data structure. I mean, think about the work on data flow languages, for example. Whereas this account model, I mean, I find it very fitting that it's used as an introductory example for object-oriented programming very often, is really a very imperative object-oriented model. And, well, you have to think, we want to implement all this in a concurrent and distributed setting. So now you have an imperative structure which is based on mutable shared state. And at the same time, you say concurrent distributed computing. When you hear these words in one sentence, my advice, run. Otherwise, there's a lot of pain to be had. A data flow graph is just something where it's much easier to reason about behavior once things get concurrent and distributed. And we can also talk about performance and parallelization, but let's not do that here. We are really interested in the programming language on top of that. So how do these systems differ when I want to add this custom validation functionality? And here it's really historically the other way around. Actually, Bitcoin already introduced this data flow structure, the UTXO graph. And then the second generation system, Ethereum, went to account-based style. Why? Because Bitcoin actually doesn't have a lot of scripting capability. It's quite minimal. But Ethereum has a lot of scripting capability, so much so that you can produce endless headlines of exploits and things going wrong. Very powerful. So, is it inherent? Is it just that this data flow graph, you just can't script it in a very expressive way? That's good because you don't get fewer exploits, but it's bad because you can't do much with it. Or can we somehow get the best of both worlds? So let's look at how validation works in a bit more detail with these data flow graphs, unspent transaction inputs. So there are transactions that are these are the boxes, and their inputs and outputs. And as we've seen before, the inputs is the funds or data that's being consumed, and the outputs is what you can spend from a transaction. Now, in order to link two of these transactions together, we have to validate that this connection makes sense. This works by attaching to each output, not just the value which is being transferred, but also something called a validator script. That's a piece of code which says, well, I'm willing to connect to this input or not. And the input contains something called a redeemer or witness, which is a piece of data or code which proves that it has the authority to spend, for example, those funds or make use of that data. And how is validation happening? Very easy. Function application. You apply the validator script to the redeemer argument. If the whole thing evaluates to true, all good. Otherwise, reject the transaction. That's very simple, but it's also very localized. You can't make any interesting decisions at this level. So what we've done, we have taken this model and we've extended it slightly. So we've said, well, for every output, instead of just having the value and the validator, we also add some extra data on top of it. So there's some information which flows with the value. And also, the validator gets access to some of the state, in particular to the entire transaction that's being validated, not just to the redeemer of the spending input. Now, once you do that, the function application is a bit more complicated because the redeemer gets applied to a few arguments, but it also has a lot more context to make a decision about judging a connection to be valid or not. So we call the resulting model the extended UTXO model. And it is structurally, it exactly preserves the data flow in the original data structure. So that's nice about it. All the good properties of UTXO are still preserved. But it greatly increases the expressiveness of the scripts which we can write on top of this. So in particular, we have data flowing with values. And just as a kind of guide, we are talking about having an imperative object-oriented model like Ethereum, which we want to represent in a functional way. Like for compilation, we know how to do that, right? If you have a stateful computation, you use a CPS conversion and you hand all the data through, thread it through your program, same thing. Like we know that for a long time. Can't we do the same thing on a blockchain? So we take these stateful updates on the account-based ledger and we just thread it through the data flow graph, applying something like a CPS transform to the code. Should work out, right? And also, by separating the scripts from the data in the outputs, we get a form of identity because these scripts, they're always hashed. They're represented by their cryptographic hash, which, well, is unique. That's the whole point about the cryptographic hash. And so it gives us an identity for these scripts, which is the other thing that the account-based model provides. And finally, by having this additional information about the transaction, scripts can actually reason about not just where the validator reasons about the input that the connection is being made to, but also the outputs from that same transaction. So basically, how are those funds spent in the future, maintained in the future? So now we can use that to assert invariance properties for validation which span multiple transactions, so in transaction chains. So that allows us to lock funds, for example, say these funds can only be used in the future under this scheme if X, Y happens. So it's not just a local decision, it becomes a global decision. So we can encode all these things, and that makes it much more expressive. All right, so this is how we have kind of boosted the scripting capabilities of this functional data structure. So, but maybe the major point is, well, when I ask who has written Solidity program before, a few people raised their hands, but most of you haven't. So let me explain it as a small example. Let's have a simple crowdfunding example, okay? So somebody makes a crowdfunding campaign. I'm going to produce a video about XYZ if enough people pay me money to pay for the production kind of thing. And so they stipulate a particular deadline by which the funds have to be raised. And then a certain goal which has to be reached in order for the crowdfunding to be successful. And then if the goal is not reached or the campaign owner doesn't collect the funds, then we have to have a deadline where people can get a refund. And that's the entire set of rules. So if you want to implement something like this, people call it a smart contract. They're not particularly smart, they're just pieces of code, but they're contractual. And so if you implement this in Solidity, well, you write some Solidity, strange language, and then maybe you think you're done because you did the implementation for all the validation stuff and so on, or everything that happens on-chain. But no, you have to write JavaScript too. And actually, you write typically more JavaScript. And also, the two are connected in a very weird way. There's a JavaScript library called Web3.js, and the JavaScript code runs in the client's browser, and it talks via this Web3.js through a local node of the blockchain and via a JSON protocol. And really, if you come from a programming languages background, you see this kind of thing, you say, well, this is actually a stage, a two-level programming model. Why am I using JavaScript and Solidity in an ad hoc JSON connection? It's very inconvenient. You have to use two programming languages for starters, both of which are questionable. It's very complex because this protocol comes in between. If you have some code, which happens very often, the on-chain code you pay for, its execution needs to be paid for as part of the transaction fee. So it's actually costly. So you don't want to do expensive computations there. Now, if you find that some of your Solidity code is too slow and you want to move it out to the JavaScript, well, you have to rewrite it because two different languages, not very convenient. And it's very fragile because there are, of course, interfaces between the functions in both sides. And, well, if they don't match up, well, you know what happens in JavaScript land. Things just don't work. So we thought, no good. We'll do something more principled. Realizing it's a two-level programming problem, let's use some more powerful programming language. So the off-chain programming, let's do that in Haskell. And you know what? The on-chain program, let's do it in Haskell as well. Well, actually in a subset of Haskell, but Haskell. And then we use meta-programming instead of some weird JSON protocol to connect the two. So we get one programming environment, one program, which is staged. The outer part for the off-chain code, the inner part for the on-chain code. Then we can move code between the two. So it's integrated. It gets much more compact. And it also gets much more robust because there's actually a type checker looking at both pieces of code and making sure they fit together. That's a big win. So let me show you how that looks like. So this is, again, our crowdfunding campaign, and this is the function where you contribute some code, some funds. All right, so you have a function, it gets a campaign and a value as an argument, and there's a monad in which this whole thing runs. And so we want to make sure we only have a positive contribution. Then this off-chain code, it gets a public key from your wallet in order to spend some fees. And then it creates a script. And we'll see how that script code looks like in the next slide. But let's create this transaction first. In the transaction, we specify what's the script code which is going to validate this transaction and the spending of those funds, the value we want to contribute, and then our own public key as a reference of where a refund can be paid to. Remember, in this UTXO model, payment just owning funds means you can spend them. So if you lock them with your own key, you're the owner because you're the only one who can spend them. And then we register a callback, and for the case that the campaign deadline expires and we want to look into whether we can get a refund or not. All right, so that's the off-chain code. And then the on-chain code, well, more Haskell. But this code, this is now meta-programming. It doesn't do anything. It constructs a program using template Haskell. So it's parameterized by the campaign. And then if you are not familiar with template Haskell, ignore the fancy brackets and dollar signs. What that basically means is, well, we want to use the Bluetooth Core compiler, Haskell to Bluetooth Core compiler, and implement the following Lambda abstraction, which gets a campaign, action, what's to be done, and the contribution. And now we want to validate whether this contribution can be spent. It can be spent in two cases. Either the campaign is successful, or the contributor can get a refund. So it makes sense to have a case distinction between these two cases. If we are in the refund situation, well, then it must be after the collection deadline in order to get a refund. And only the contributor can be a beneficiary of this transaction because they are the only one allowed to get a refund. And the transaction has to be signed by the person whose public key was given in the contribution. Okay, that's all we need to check. So if the campaign owner wants to collect the funds, well, it has to be after the campaign deadline and before the collection deadline. So in this time window where we can check, are there enough funds, can we get them out? And obviously, the sum of all funds paid in has to be bigger than the campaign goal. And if that's the case, and again, the signature on the transaction works out, we can spend those funds. All right. So that's how this looks like in Haskell. Now, what's the overall story here? Well, the overall story is that given this code we've just seen, that's the Haskell code you write as a Plutus developer. Well, you're just writing Haskell. You're a Haskell developer using a particular set of libraries and tools. And you want to run this on the Cardano blockchain, say. Then you use GHC with our libraries and plugins. And this compiles into off-chain code, which may be in JavaScript or WebAssembly or something that's cross-platform, and it embeds the Plutus core code in a serialized form that has been generated by our compiler. And now, if you, for example, want to contribute to this crowdfunding campaign, then this off-chain code runs the Haskell code we've just seen because you click on something in your wallet, and that submits a transaction to the blockchain. That transaction is added to the chain if it's valid, and its output is logged with a little bit of Plutus core. That's the validation script. That's the stuff which we wrote in template Haskell. And if somebody wants to spend that, then they have to validate against that, that Plutus core, that validation code. And also the wallets, the offline wallets, they are notified of new transactions coming in because they may trigger one of these callbacks, these events, which we've seen one, where we registered for checking after the campaign deadline whether a refund is possible. So that's the overall setup of the system and how the two levels fit together. All right, so what about the status of this? Well, currently Plutus isn't integrated in the Cardano blockchain yet, but again, because of our development methodology, we can still run Plutus code. So how are we going to do that? Well, we've got something we call lovingly the mock chain. And what that is, it's just a functional emulator of the function behavior of the blockchain. So specifically, it's a trace-based, an event trace-based system which runs the Plutus on-chain and off-chain code, which is compiled in exactly the way which I've shown you before, and executes it in a way that you can see what happens if you run that actually on a UTXO ledger. And this is really only possible because we have this semantics-driven development process where we know the exact functional behavior of that blockchain. If we would try to do something like that for Ethereum or so, it would be quite complicated because you have to replicate the semantics of all the different bits and pieces, including the virtual machine, which basically means, well, you have to look at the C++ code and see what's going on. We've got the semantics of these bits and pieces in the form of LaTeX and executable specifications in Haskell, and that allows us to build an emulator like this quite easily, actually. And all this is also based on some papers which are in this library which I've mentioned before. All right, so that's nice. So you've got this emulator. Can you use it? Can you use it? Yes, you can use it. So in fact, we've got an online little web app which is called Plutus Playgrounds, which allows you to write these Plutus contracts and run them. And I just want to quickly go through an example of this crowdfunding campaign. So here this is the code of which you've already seen a snippet on previous slides. So that's a data structure which describes the campaign. It's just a record which specifies the various parameters. So what's the deadline, when have the funds to be collected, what's the target, so the goal of the crowdfunding campaign. Just normal Haskell code. Then further down, the two actions which we can perform in this contract is either contributing or getting refund or collection. And then if we are going down a little bit further, that's the contribute function, which I've gone through on the previous slides. So I'm not going to explain it again, but just highlighting, it's the same code. And then at some point, we have to tell the system what are the Haskell functions, the off-chain functions, which a user can use from their wallet, from their client code of the ledger. And so we have a little bit more of template Haskell where we mark these top-level functions, which we can use externally. All right, so now we can compile that code. And as a result, we get a setup of multiple wallets. So this is an emulator, so you're playing all parties at once who are involved in the system. And so by default, there are already 2 wallets with some initial funds. And for this example, we add a third one. And then inside the wallet, there are these buttons, which you see one clicked in a second, which are the different endpoints. So the 2 top ones correspond to these 2 functions, which we highlighted in the end in the Haskell code. So that's the bits of functionality from the contract code, which I can invoke from the wallet. The third one is just the normal payment. And so I click on one of those, and that gives me an action. So I said we use an event-based trace. So what I'm doing here, I'm building up this trace by specifying various events or actions. Now, the first one is that as a campaign owner, I have to define a campaign. So I'm specifying how long does it run, what's the target value, what's my public key. And then as 2 people who contribute, we also add 2 actions, and I'll spare you me filling in the form. And both of them, so the target here is 10 ADA, and both of them contribute 5, so the campaign should be successful. And then we also need a wait action, because the campaign runs for a certain time. And just doing these 3 transactions will take less time, so the result cannot be collected. And the trigger in the contract code, which waits for the campaign to be successful and take the funds out, isn't triggered unless I wait a few more transactions. That's what I'm doing here. And then I can submit this event trace to the mock chain using on the basis of the Haskell code we had before. And then we get a visual representation of the UTXO graph with the various transactions, some logging information if you need to debug the contract. And that's the final set of balances. So all started out with 10 ADA, but now the first one, which is the campaign owner, has got 10 extra due to running this campaign successfully. All right. So this is how it works. Now, I've argued for a research-driven development process because that's what we really need in order for building an application where proper working of all these various pieces, cryptographic algorithms, protocols, distributed protocols, implementation, all has to come together, and we have to have reasonable confidence in that it's actually doing what it's supposed to do without having to patch every second day. I outlined how we can take this data flow ledger model, extend it such that we can preserve all the nice functional properties of that ledger model, but get more expressive scripting capabilities. And then how we can replace this mess of some off-chain JavaScript, on-chain other code by an integrated program approach based on metaprogramming. And if you want to try this playground thing out for yourself, well, it's online at the IHK testnet site. And if you want to have a look at the source code, all our work is open source. So you can check it out on GitHub, and the URL for the papers I've given before. And if you're interested in more details, we had this Bluetooth Fest at Edinburgh University in beginning of December. And this website has all the videos from that event and a lot more detail if you're curious to know more. Thank you very much for your attention.
We have time for questions.
Hey, I know it's Nicky. I will ask two, okay? First one, do you have any notion of privacy in there? Is that, or is everything public and visible to everyone? And second one was, if the owner of a campaign doesn't click refund, will I ever see my money back?
Okay, good questions. So number one, first question was, what about privacy? So now Cardano, as I outlined it here, is a so-called public blockchain. So it's like the public internet. Everything is visible to everybody. If there's some data you don't want other people to see, you can always encrypt it. Now, IHK is also working on a permissioned enterprise version of Cardano, which, surprise, surprise, is called Cardano Enterprise. And that has a permissioning system, fine grained. So we are working on both types of systems. And I think there's still the community and also from a technical understanding, like what's the trade-off between these systems? Is it sufficient to just use encryption on a public ledger? Do you want these private ledgers? I think that's a broad discussion, which we can have over beer, but probably won't finish here. But yeah, so we're working on both types of systems. Secondly, what about the campaign owner not clicking the refund button? So I'm sorry if that didn't become totally clear in the presentation. The refund is actually triggered by the people who contributed. And the way it works is that in the code, in the Haskell code we saw, not in the playground, but on the previous slides, we had the actual code, and then there was a registering callback. And that registering of the callback, or maybe I didn't show this, so that's part of the implementation of the contribution, is registering a callback for the deadline of the campaign. And once that callback code is invoked, it checks, has the campaign claimed the funds? If not, submit a transaction reclaiming the funds. So it is fully under control of the contributor to get the funds back. And no collaboration of the campaign owner is necessary, which is important because otherwise, well, people run away.
We have time for one more question.
I apologize, I can't help myself. You complain about the lack of formal semantics and solidity, and then you present Haskell as an alternative, which last time I looked didn't have a formal semantics either. I appreciate Haskell's formal superior design, but I mean, especially if you add template Haskell, you have significant complexity there. Why is that not a problem?
So the solidity is the on-chain code, right? So I didn't complain, although I do that very often, about the lack of formal semantics in JavaScript, which would be the equivalent of what you just said. So solidity is the code which is used for the on-chain validation. Now, in our case, it's not the entire Haskell program which is used for on-chain validation, but as I said, there are the two components. There's the off-chain code, that's actually most of the Haskell code, and then there's the on-chain code, that's only the little predicates which were in the template Haskell brackets. Now, this is the code, this is only a subset of Haskell, what we call Bluetooth TX for transaction language. And this is compiled to system F omega. And for this part of the system, which is the bit which is the, where we really want to know exactly what the semantics is, we don't use full Haskell. We use this restricted language, and we have a translation which we are also in the process of formalizing about what source level Plutus TX code gives us what system F omega code, and of that we know the precise semantics.
Thank you very much, Manuel. And it's time for our first lunch break. Thank you.